we start recording. There we go. All right. And then, I might as well just switch back to my OneNote. And away we go. All right. Next lesson. Can everybody go to example 4? Adding and subtracting. All right. Add the following. Well, right now I can't. You know why I can't? Because they're not like terms. I always like to do this little conversation when I do this lesson. I like to say, okay, think about this for a sec. Remember when you were in grade maybe 3 or 4 and you were first learning to add decimals? And let's say that your little brother or sister's in that grade right now, and they came home with their homework and they said that. What would you tell them they did wrong? You'd probably say something like, "Oh, you messed up place value, right?" Wrong. You messed up place value. Okay, so what if? Now how do I get back to black? There we go. Black. Are we back on black? Black. What if your little brother or sister in grade 7 did that? Oh, hang on. 2/5. What if they did that? What would you say? You'd say, you need a common denominator, right? And again, you'd mark that as wrong. Ooh, that's a fancy pen. And what if you got all kinds of, you have a lot of siblings. I didn't realize how big your family was. You have yet another sibling who's in grade 7 learning algebra for the first time, and they think this. They're wrong again, right? Not only do you have a lot of siblings, they're not great at math. Luckily they got you. So, can I point out to you something that maybe you've never thought of before? All 3 of those mistakes are the same mistake. You're thinking, well, no, this is a decimal mistake, right? I forgot about place value. I forgot about common denominator. I forgot about like terms. No, actually, that third description fits all of them. You can't add things unless they're like terms. That's all the same mistake. This and this aren't alike because of place value. This and this aren't alike because of denominator. And this aren't alike because they're not the same degree. So you've learned all of these things. Maybe even this one too. Anybody do this when they were in grade 7? Right? You can't do that. Also wrong. Well, here's the next wrong. I can't add those together. That's just wrong. I can only add alike things. That's been true in math since you were in grade 1. You just didn't realize it. Right? You can't add apples to bananas and say it's an abana. So with that in mind, can I add those 2 things? Not like that I can't. But I notice that 50 is 5√2. Now I can add it. That is 8√2. Because think of it, if you like, as 5x plus 3x. Together that makes 8x. So once you've simplified your radicals, you can start looking for ones that you can collect as like terms. Cool. So let's do that for this one. Negative 18 is like saying negative 3√2. 50 is 5√2. 27 is, it has a 9 in it. So the 9 comes out, becomes a 3, so that's 6√3. And I can't do anything with 4√5, so it stays the same. Where are my like terms? Here and here. Can I add the other ones? No. There, that's as simple as that one gets. Now we're going to add algebra to the mix. So, let me know if I'm going too fast. I kind of want to. We're going to plow through 3 little sections here. Root 20 times x is like saying 2√5x. 45 has a 9 in it. If the 9 comes out, it becomes a 3. 3 times 3 is 9. And it leaves behind 5x. Hey, look at that. Those are like terms. Negative 7√5x. It's like root 5x is its own variable. Why are you not doing notes. Hello, we're doing notes. What are you doing? You done all these already? Oh, okay. You got ahead of me on the notes? Okay, that's fine. Whoa! Check that out. All right, what's the biggest perfect cube in a to the 4? Well, I'll do this one in 2 steps. It's got an a cubed times a in it, so there's the perfect cube there. And this one, 27 is a perfect cube. So let's leave it alone. All right, this a escapes its radical jailer, and it becomes a. And this 27 escapes its radical and becomes a 3. Now, this root here and this root here are like terms, but can I add a and 3? No. Is it 3a? No, that's 3 times a. So you can kind of make the argument that maybe that's done. You can't really add it. But, you know, you kind of can too. Is it cool to you if I show you that it looks like this? What do you think of that? The argument could be made that you didn't make it simpler. You made it more complicated because now it's got a bracket in it. But the argument could also be made that, yeah, but this is one number times a root. It is sort of simpler. The important part is, do you understand that this thing and this thing are the same thing? That's what it comes down to. Can you recognize that those are the same expression exactly? Because that's how algebra goes. I spent my whole slot 1A this morning doing problems, helping people out with their calculus homework. It was not the calculus that any of them were stuck on. It was, I did the question, my answer doesn't look like the book. Is it the calculus that they've done different? No, they just didn't simplify it the same way. The answer in the book said this, and they said that, and it's like, I don't have the right answer. So it comes down to just knowing how numbers behave, knowing how algebra works. Okay, cool. So that takes us to the end of that page. And now there's a page called, just like that page 7 we just went over, it's a you try. So this one's for you. Don't start it now. Let's do something else. Can you jump to 5.2? We just did adding, and really adding and subtracting is the same thing, right? Subtracting is just adding negatives. Let's do multiplying. All right. Multiply the following. We have 2 root 7 times 4 root 75. Now, you can almost think of this, if you like, as really 4 things being multiplied together. I know it's 2 brackets, it's 2 things. Yeah, but it's kind of 4 things. It's 2 times 4 times root 7 times root 75. Now, you can combine those 2 radicals. Wait a minute. Like, you just said it was wrong if I did this, right? That's wrong. How come this is right? Because it is. Why the difference? What's with these radicals? Well, remember what a radical is. A radical, remember this from grade 10, is really a fractional exponent, isn't it? And exponents have something called power of a product law. Remember back in grade 9 you learned your power laws. If I have 2 variables to an exponent, I can distribute the exponent. That is not true for an exponent on a sum, right? Does this equal that? You know darn well that that doesn't equal that. This thing actually equals this, right? You have to have a 2xy in the middle because of foiling. Remember that? So there's no such thing as power of a sum law, but there is power of a product law, which means I can go that way. If I see 2 things to the two different bases to the same power, I can combine them as 1 power. And that's really what I just did here, or what I'm about to do here. It is 2 times 4 is 8 times the square root of 7 times 75. Oh man, quick. What's 7 times 75? 3 75s. 2 75s is 150. So 4 75s is 300. So 6 75s is 350. 350 at another 50 is 400. 425? I think it's 425. Am I right? 425? 525. Oh, I counted wrong. So it's 8 root 5. Oh, no. Sorry. 8 root 525. But simplify after your multiplication. Okay, I will. So my simplify would be, okay, what's the perfect square in 525? It's got a 25 in it. So I'm going to take the 25 out. It becomes a 5. So 5 times 8 is 40. Oh, man, how many 25s in 525? Let's see. There's 21. 21 times 25. That sounds about right. There's 2 of them in 50. Carry the 2. And then 125. Yep. Any perfect squares in 21? Maybe I'm not finished. No, 21 is just 3 times 7. No perfect squares there. Okay, that was actually kind of hard. They call that method 1. You know what I like better? Method 2 is to simplify first. How about before I even set foot in this multiply, why don't I simplify the 75 first? There's a perfect square in there to begin with. This 25 is in there. Wouldn't it have been easier to do it this way? I'm not saying you have to do it this way, but I think that's way easier because the numbers are smaller. Remember, we're going to test you on this stuff without a calculator. And 2 20s and 3 7s is a heck of a lot easier than 7 75s. So I think I like this way better. What do you think? It works to do the multiply first, but I like simplifying before I start messing with the multiply. Agree? Oh, you don't have to agree. It's your thing. Okay, anyway. Next, we have this little thing right here. This is kind of like an algebraic rule, right? The coefficients just multiply together, and then you can, as long as it's the same, this is important, as long as it's the same index, it's the same root, you can just combine the roots when you're multiplying. Assuming, of course, that a and b are bigger than 0, because again, you can't multiply, or you can't square root negatives. All right, let's try another one like that. Multiply and simplify the following. Well, right now, that doesn't simplify. There's no perfect squares in 3. There's no perfect squares in 6. But notice that 6 has a 3 in it. So when I multiply it, those 3's together make a 9 factor, and the 9 factor comes out. So you get 15 root 2. Yes, if you left an answer as 5 root 18 instead of 15 root 2, you lose marks because it's not simplified. All right? Just because I'm in radicals doesn't mean distributive property works any differently. This is 2 times 4, which is 8. The cube root of 11 times the cube root of 2 is the cube root of 22. 2 times negative 3 is negative 6. The cube root of 11 times the cube root of 3 is the cube root of 33. Can I simplify that anymore? No. Any perfect cubes in 22? No. There's no 8s, no 27s. Same thing with 33. We're done. That does not simplify anymore. Okay. Next. What if it's a binomial times a binomial? This is just good old FOIL from grade 10. So remember what FOIL stands for? F is for first times first. 4 root 14. O is for outside times outside. 4 root 2 times 5 root 14 is negative 20 root 28. Inside times inside is 3 times root 7, which is 3 root 7. And last times last is going to be negative 15 root 14. I see 2 things I can do here. I see like terms. Do you see them? 4 root 14s minus 15 root 14s. That's negative 11 root 14s. What else do you notice? One of the key things to being good at math is to be able to notice when you can use one of the tools from your toolbox. What do you notice about the 2 terms that I have left here? They're not like terms, at least not yet. What do you notice? You have to be able to know this. I can't notice things for you. What do you think, Mudassar? 28 simplifiable as a radical, as a square root. 28 has a 4 in it. So when I take the 4 out, it becomes a 2, which makes this minus 40 root 7. Hey! Now those things combine. So I have negative 11 root 14 minus 37 root 7. And you know, if you've got time to kill, and you have a calculator, which we won't let you have on the next test, but say you're doing your homework and you're looking at something and it's like, is the answer key wrong? I really think I got this. Run that through your calculator. Run this through your calculator. You should get the same exact oogly irrational decimal. Has to be. They're the same. I followed the rules and they are the same. So there we go. There is my operations on radicals. You try one. I'll give you a sec. While you're doing that, I'm going to do attendance. I haven't done attendance yet. I'm going to say hello to people at home. Hello, people at home. Do-do-do. People watching this on video could, of course, just, speed up through this part. Oh, I didn't do slot 1 attendance either. Oh, man. Okay, who was here? Haugen was here. Sabrina was here. Nevada was here. Okay, next class. You guys. Take attendance. Ludisser's here. Paul's here. Matt's here. Isra's here. Jessica's here. Ashwin's here. Arno. Pam. Jamin. Annie. Maggie. Shangru. Time. Early. Shanglin. Joe. Lisa. Oh, Joe. Joe, you're the other guy who wasn't here. Did you bring a lunch today? No. Well, when are you going to write the test that you will need? Do you have any spares in your day? Did you not? Is that not? Do I have you down wrong? Were you not here last class?
No, I was here.
You were here? Oh, okay, then I don't. Oh, and that maybe that's not you. Okay, I'm gonna have to check my records. I have you on the board. Do I have another Joe? Maybe I do. Confused. I have too many different classes. Okay, anyway, there we go. Boom, boom, boom. Attendance done. Okay, all right, done attendance. That should have been long enough to play with that question. Let me go back to my Teams meeting so I can see. Guys at home, if I'm going too fast or if something's not making sense to you, feel free to put up your hand, which means you can just turn on your volume and ask a question. Okay, so did you get 35 root 15 minus 42? What? What happened there? I could have done that in 2 steps. Root 3 times root 3 is root 9. What's the square root of 9? But, you should recognize very quickly that any root times itself is that. Has to be. Okay, so that's how I did that. So that's going to be 35 root 15 minus 3 42s. You should be able to do that. 3 40s, 3 12s with a 0, or 12 with a 0. So that's 120 plus 6, so 126. Can I simplify that anymore? No. 15 doesn't have any perfect squares in it. All right. There we go. Once again, the next page is a you try. So this is part of your homework. We will correct this when I see you next class. But we got one more thing to do. Since we've seen multiplication, let's do dividing. So it's like, hey, we did adding, but subtracting didn't get its own page, because, subtracting is just adding negatives. Well, multiply is just, or sorry, I should say that again. Dividing is just multiplying reciprocals. Why does it get its own page? Well, because there is some complications to dividing. First of all, check that out. Divide the following. Well, I can think of that as kind of 2 separate divides. 8 divided by 4 times, and then think of it this way. And again, you might be going, huh? Why are you allowed to do that? Well, because once again, grade 9 math gave us this rule. Product of a quotient. You can distribute an exponent through a divide, which means you can go backwards. If you see a divide where you have 2 bases to the same power, you can put them into 1 power. And that's really what I just did there. Roots, radicals are powers. They behave according to exponents in BEDMAS. So this is 8 divided by 4, which is 2, and the cube root of 3. And there's the rule written sort of algebraically as a rule. Do we get that on the formula sheet? No, sorry. For whatever reason, the powers that be decided that's not a formula. It's just an idea that you have to understand and be able to use. Okay, so let's try this one. Well, once again, I can combine. Everything here is under a square root, so there we go. Everything's under a square root. And then 24 divided by 3 is 8. And x squared divided by x is x. And if I leave it like that, I've lost half a mark. How come? Because 8's got a 4 in it, right? There we go. Now it's time for what I like to call math etiquette. Math has etiquette. I'm sorry, but it's just rude leaving that as your final answer. You know better than that. You'd leave it as 1/2. You'd never leave an answer as 5/15. You'd leave it as 1/3. And then there's situational etiquette. If I am doing just algebra and my answer comes out to be 7/3, I think I'd leave it as 7/3. But if it's like a word problem where, I don't know, it represents cups of flour in a recipe or something, nobody has a recipe anywhere that says 7/3 of a cup of flour. So you would change it to 2 1/3. It's etiquette. It's politeness. We very much care about being polite in math. It's really just what's the easiest way to look at the numbers. Well, we don't like radicals in our denominator most of the time. So we are going to do something called, come on you, rationalizing the denominator. In the olden days before calculators, when dinosaurs roamed the earth, dividing by a square root or some other radical was really difficult to do by hand. Try it yourself if you don't believe it. What's 2 divided by the square root of 5? Well, how many decimals on the square root of 5 do you want to play with? There's what your calculator would spit out. Could you imagine trying to do that divide here? Let's just give it a go. Let's do it with 4 decimals. 2.236 into 2. Do you remember how to do stuff like that? You have to match how many decimals are in both parts of your divide. And then you go, okay, well, 2 doesn't go into 2, but 2.236 does go into 20 once. So that'd be not once, what am I saying? 9 times is what it would go in. So now I got to do 9 times 2.236. And remember, I don't have a calculator. So what is 9 times 2? You know what? I'm tired of this already. I've had enough. We don't want to do that. But on the other hand, what if it was the square root of 5? I said, hey, come back. What if it was the square root of 5 divided by 2? That's not nearly as hard, because now the 2 goes here, and big wonky decimal, you don't have to play with the big wonky decimal. You just have to put numbers into it. 1, bring down the 2, but the decimal goes there. 1, bring down the 3, 1, bring down the 6, that's a 6, 8, and I could do this all day. This isn't hard at all. There's an enormous difference in calculating brain power to dividing with or dividing into a radical versus dividing with a radical. I don't want to divide with a radical, but dividing into it, no problem. So that difference in amount of work and amount of brain power and amount of calculation meant that we just don't want to have radicals in the denominator. And even though everybody has a calculator on, several devices on you right now probably have calculators, it's still kind of a drag to divide by a radical if you can avoid it. So what we do is we say that is not simplified. It just isn't. I want it to be simplified. How do I simplify it? Well, there's 2 main techniques. Actually, there's 2 main techniques? What the heck's the other main technique? Okay, as far as I know, there's only one way to do this. I'm going to do it my way. It's called multiplying by the, what? Yeah, I don't know. I have no idea what they're telling me to do. There's one way to do this. Here, it's the same thing as here. I think we've had this conversation before. Think back to fractions. What do I do to add those? I get a common denominator. Great, I'll do it for you. The common denominator is 6. And the answer is 7/6, or 1 1/6. Now, this is the question that people get wrong all the way to grade 12, and it makes me laugh. What did I do to turn this into this? Don't fall for it. You know what people always say? They say they say that you multiplied it by 2. Really? 2/3 times 2 is 4/6? No, it isn't. It's 4/3. Then they usually go, okay, wise guy. What I meant was you times the top and the bottom by 2. Okay, so now think about that. If you times the top and the bottom by 2, and I agree with you, that's what we did. What did you really multiply by? 1. And that's a hugely important idea in math. The property of 1, the principle of multiplying or dividing by 1, is an enormously big tool in your toolbox. It is the best tool in your toolbox because it allows you to change anything into any form you might want it to, as long as you only multiply or divide by 1. Because timesing or dividing by 1 doesn't change what the number is. So that's what I'm doing over here. I'm going to take this thing and I'm going to multiply it by 1. But here's what my 1 looks like. That's 1, right? Anything divided by itself, as long as it's not 0, is 1. Would you like to draw a 1 around it? This is what I like to do. I like to draw a block letter 1. There, 1. Oh, that didn't work very good. Undo, undo, undo. Undo. Let's try it again. There, 1. Okay, you get the idea. So that's 5√7 over, and we just had this a second ago. What's root 7 times root 7? It's just 7. There, rationalized denominator. We've already kind of run into this year. Do you remember where we hit this before? Remember it from trig? Right? In trig, what's the sine of 45 degrees? Well, according to my unit circle, it's actually 1 over the square root of 2, but we don't like the answer like that. So we always called it root 2 over 2. Where did that come from? By timesing by 1. Ah, so we've seen this already. And you might have saw this in grade 10. But anyway, the second technique, oh, I get it. This is the only technique for, oh, I thought they were saying there's 2 techniques for example 7. No, no. The second technique is for example 8, and it's called multiplying by the conjugate. That's the word they want in that blank. Conjugate. I don't know where that word comes from or why it means what it does. The only other place I can think of is you can conjugate verbs in languages, right? Remember that? Anybody studying French? Conjugate your verb, right? Nous sommes, vous êtes, all that. You're conjugating verbs. Prisons have conjugal visits. Don't know what that has to do with anything, but there's that same word. Okay, here's what a conjugate means. Remember this, guys? Factor that. What do you get? Oh, don't all shout it at once. Come on, what do you get? There you go. You get a minus b times a plus b. And if you were listening carefully when we did this, I think I called those conjugate pairs. They're not opposites exactly. The opposite of a minus b would be b minus a, right? They're not quite opposites. They're the same 2 numbers plus or minus. They're called conjugates. That's what I want over here. I would like to multiply by 1, but my 1 is a conjugate. Once again, this is my 1. That's my 1. A big fat block letter 1. Okay, that probably just makes it look uglier, so I'm just going to make that go away. Okay, so you know what you probably should do when you do this, though, is you should probably put this in brackets so that we can tell what's happening. That's going to be 9 root 3 And 9 times 4 is 36. But what is happening in the denominator? Well, okay, go back to what I was showing you a second ago. If you started here, you are going to get that when you multiply. How come? Because there won't be an AB term because they end up canceling, right? I could show you if you like. We can do full FOIL. Root 3 times root 3 is 3. Root 3 times negative 4 is negative 4 root 3. Root 3 times positive 4 is positive 4 root 3. And 4 times negative 4 is minus 16. Notice those two things are opposites. What happens when you add opposites? They cancel. That's why when you multiply conjugate pairs, you get a difference of squares. There's no thing in the middle. So those go away. So you're going to get 9 root 3 minus 36 all over 3 minus 16, which is negative 13. Now, would it freak you out if you were doing a question like this in your homework and the answer said this? Are you cool with the fact that that's the same number? What happened to it?
Multiplied -1.
Close. I factored negative 1 out of the numerator and canceled it with the negative on the denominator. But has the same effect as what you just said. So yeah, either of those is a good answer. But again, it comes down to recognition. If you were doing your homework and this was what you got and this is what the book said, would it be like, oh, I'll never get it, never? No, you gotta just use some logic and reason in your number skills and realize that, no, I've got the right answer. It's just a slightly different form. Do I care? Not really. They're the same answer. And that's it. That's the skills we need for radicals. Again, guess what the next page is? It's a U-try. We'll go over it again next class. So is the page after that. You get two U-tries. And then next lesson is going to be about more algebra with radicals, radical equations. So that's the end of my little lesson. I'm going to end my video now. And I guess we better get ready to finish off your test, eh? Okay, so people at home, you can probably log off now.